Welcome to our MECH 1000 video for Blueprint Reading Unit 8. In this unit we are going to be looking at section views. So section views are used in drawings when the part in the drawing has some internal features that need to be shown in greater detail. I like to use the analogy of taking an apple and cutting it in half, and then you can see the core of the apple and the seeds, the things that you would not be able to see if you had not cut the apple in half. So the location where you cut through the object is shown with a cutting plane line. Sometimes the cutting plane line is omitted if it's clear that the object is symmetrical and the section line has been, or the cutting plane line passes through the line of symmetry. But in most cases, the cutting plane line is shown with arrows indicating the line of sight, the direction in which you are looking after the part has been cut open. And the cutting plane line is also usually labeled with letters so that you can see the corresponding section view elsewhere on the page. So here are a few examples of a full and half section. Now, a half section is not to be confused with a half view, which we have talked about earlier, in which only half of a view is shown. And that's done in the case of where you have a part that is symmetrical, and so the other half of the drawing can be omitted without sacrificing any information. A half section is where you have the full view here, and the cutting plane line is drawn in such a way that in the section view, half of the view is a section view and half of it is not. So we can see here in this half section example, the top half is a section. We see these diagonal section lines indicating where there is solid material that has been cut through. And in the bottom half, we see it without the section lines. We see it as we would just a regular side view with hidden lines indicating the features that are internal to the part. Over here we have a full section view. The cutting plane line is the vertical line here that passes straight through the object. There are a pair of arrows at either end indicating that we are looking at the left half of this object when we're looking at the section view, and the letters that label it indicate AA. That means that this cutting plane line corresponds to section view AA. Okay, let's look at an example exercise. In this question, we're being asked what type of section view is being drawn. So this is an example of the type of section view that I mentioned where the cutting plane line is not explicitly shown. But we can see from the relationship in the layout of these two views that they have a similar relationship to a top view and a front view. So these views are projected. The section view is projected from above, and it is projected in a direction perpendicular to the cutting plane line. So the cutting plane line slices across the top view in a horizontal fashion, and then that view gets projected down perpendicular to the cutting plane line, and that's why we see it down here. And we're looking in this upward direction. So what we are seeing here, what type of section view is it? We are seeing a full section view, complete from side to side. Both halves have section lines in it. So it's a full section. Does the cutting plane line pass along the vertical or horizontal center line? As I said, based on the relationship of these two views, that cutting plane line would be right here. It's not shown, but it's implied that it's passing through the center of the object, so it's passing through the horizontal center line. And which half of the part are we seeing? Again, we are cutting through here and looking up. And how do we know that? Because they have the same relationship as a top and front view. In orthographic projection, when you look at a top view, the bottom of it is the front. The top of it is the back. And so when we look at the section view, we are looking in the same direction that we would be looking at if we were looking at it from the front. So we're looking at it in this direction, which means in the top view, we are looking in the upward direction. So we're looking at the upper half of that part. Okay, let's move on to some commonly used symbols that you're likely to see in some blueprints, including the counterbore symbol. The counterbore symbol is this block U shape, which comes from the shape of a counterbore itself, as seen in this section view. So that block U is the symbol that is used to replace an abbreviation like C-bore. The reason why a symbol is preferable to an abbreviation is because the abbreviation is language-based. This really only makes sense if you speak English. But the symbol can be interpreted regardless of what language you speak, so it's more universal. Down here we have a V-shaped symbol, as you can see right here, that is used for a countersink, and again the symbol is preferable to an abbreviation as it is more universally understood. Here we have the depth symbol. It basically looks like a capital letter T with an arrow at the bottom indicating how far down from the top surface something like a blind hole is drilled. So that indicates depth. And this symbol here that looks like a square actually means square. This type of break line indicates a cylinder. So the cross-sectional profile of this part is round, so you might be inclined to think that this also is a cylinder, and it would be perfectly understandable to think that if it weren't for the fact that we have a symbol here indicating that it is not actually round in cross-section, it is square. Okay, let's move on to yet another topic, and that is annular grooves. So annular grooves are cut into shafts. They can be cut on the inside or outside of a hollow cylinder. They are typically square in profile, and they can be dimensioned in a couple different ways. Let's look at some examples here. Here we have an example of an interior annular groove. We're looking at a hollow cylinder or pipe in section view, and on the inside surface of this pipe we have cut a square-shaped groove that goes around the inside of that cylinder, and it is dimensioned with a local note that tells us its width from side to side, as well as the depth, how far into the surface of that interior surface of the cylinder is the depth of that square-shaped profile. Over here in this example, we have another annular groove cut into the inside of a cylinder, but this time it's dimensioned differently. This time we're given the diameter of the groove plus the width of the groove. And here in the lower half of the drawing, we have two examples of annular grooves cut into the exterior surface of a cylinder. Again, it's got a square profile with width and depth indicated in a local note with a leader. And over here, we are given the diameter of the groove with its width in linear dimensions. Let's look at yet another example here. We want to know in this drawing what type of view is the top view. So in this top view, we only see half, the upper half of this part. And these lines right here indicate symmetry. It's a line of symmetry. So there is a bottom half to this top view. It's just not shown. So this is an example of a half view. not a half section, but a half view. We only see half of the part. The other half is just entirely omitted from the drawing. What type of sectional view is drawn? If we look at the bottom view, it's a section view. We see section lines on the left, section view on the right, section lines on the top, section lines on the bottom. It's sliced all the way through, from top to bottom, side to side. This is a full section view. What is the diameter of the undercut, or the inside groove? So we just talked about annular grooves, and the inside or interior annular groove can be seen right here. It's cut into the cylinder here, this bore, and there's a local note here telling us that it's 0.13 wide and 0.11 deep. So if we want to know the diameter of the bore that it's cut into is 1.19. Then we have a depth of 0.11 on this side and a depth of 0.11 on that side. So we would want to take our 1.19 plus 0.11 plus 0.11. So that would be 1.41 is the diameter from here to here of the inside groove. What is the diameter of the inside chamfer? So we have a chamfer here, but that's on the outside of the cylinder. And we have a chamfer up here as well. Okay, and it's dimensioned with a distance and an angle. So if we want to know the diameter, we have to start with the inside diameter of the cylinder, 0.99. And it's a 45-degree chamfer, which means when you have a 45-degree right triangle, the legs, the vertical and horizontal legs of that triangle, are equal to each other. So the 0.10 is equal to both the vertical and the horizontal dimension of that chamfer. So that means that we're going up 0.1 and over 0.1. So we're going over 0.10 on the left, over 0.10 on the right, and so the diameter of the chamfer is going to be 0.99 plus 0.10 plus 0.10. So that's going to be 1.19. I think this is probably a good place to stop, so I will resume this lecture in the next video.